Welcome back to Fun Facts Online. Today, we are descending into the deep, concrete caverns beneath the Swiss-French border to witness a quiet revolution in physics. For decades, scientists have been wrestling with a ghost, a fleeting, phantom atom that exists for mere fractions of a second before vanishing in a burst of gamma radiation. This atom is called positronium. It is not made of protons and neutrons like the matter that makes up your body, this microphone, or the planet we are standing on. Instead, it is a binary system of pure opposites, an electron dancing a fatal waltz with its antimatter twin, the positron. For nearly 30 years, the dream of freezing this exotic atom, of slowing its frenetic thermal jitters enough to study it with precision, remained exactly that, a dream. But in a landmark achievement that has sent ripples through the global physics community, scientists at CERN's AEGIS collaboration, parallel with a team at the University of Tokyo, have successfully laser-cooled positronium. This is not merely a technical triumph. It is the unlocking of a door that has been barred since the dawn of modern physics. With cold positronium, humanity stands on the precipice of answering one of the most profound questions in existence. Does antimatter fall down? Or, in a defiance of everything we know about gravity, does it fall up? To understand why cooling this ghost atom is such a monumental feat, we first need to understand the substance itself. Antimatter is often the fodder of science fiction, used as fuel for starships or weapons of mass destruction. But its reality is far more subtle and mysterious. The story really begins in 1928 with Paul Dirac, a British physicist of few words but immense intellect. While attempting to reconcile quantum mechanics, which is the physics of the very small, with special relativity, the physics of the very fast, Dirac formulated an equation that described the behavior of electrons. The equation worked beautifully, but it had a strange quirk. It allowed for two solutions. One solution described the familiar, negatively charged electron we all know. The other described a particle with the same mass but a positive electric charge. At first, this was dismissed as a mathematical oddity. But in 1932, Carl Anderson, studying cosmic rays in a cloud chamber, observed a track that curved exactly like an electron, but in the wrong direction. He had found Dirac's anti-electron, which he named the positron. The discovery of the positron confirmed that for every fundamental particle of matter there exists an antimatter partner. When matter and antimatter meet, they annihilate, converting their mass entirely into energy in accordance with Einstein's famous equation, E=mc². But this symmetry poses a devastating problem for cosmology. According to the Big Bang theory, the universe should have been created with equal amounts of matter and antimatter. In the first fraction of a second, these opposing forces should have annihilated each other completely, leaving behind nothing but a sea of light. Yet, we exist. Galaxies, stars, and planets exist. Somewhere, somehow, this symmetry was broken. A tiny fraction of matter survived. Physicists call this the baryon asymmetry. Understanding why matter won the war for survival is one of the holy grails of physics. By studying antimatter with extreme precision, scientists hope to find a crack in the mirror, a subtle difference between matter and antimatter that explains why we are here. While particle physicists look for differences in charge or decay rates, gravitational physicists are asking a different question. Does gravity care about antimatter? This brings us to the Einstein equivalence principle. In 1907, Albert Einstein had what he later called the happiest thought of his life. He imagined a man in an elevator. If the elevator is sitting on the surface of the Earth, the man feels his feet pressing against the floor due to gravity. If the elevator is out in deep space, far from any planet, but is being pulled upward by a rocket at an acceleration of 9.8 meters per second squared, the man feels the exact same sensation. Einstein realized that acceleration and gravity are indistinguishable. This insight became the foundation of general relativity, the theory that describes gravity not as a force, but as the curvature of space-time caused by mass. A cornerstone of this theory is the weak equivalence principle, which states that the trajectory of a falling test particle depends only on its initial position and velocity, and is independent of its composition and structure. In simple terms, a feather and a hammer, in a vacuum, fall at the exact same rate. This has been tested to incredible precision with ordinary matter. Titanium, beryllium, aluminum, and the moon all fall toward the Earth with the same acceleration. But here is the catch. We have never tested it, truly, directly, and precisely, with antimatter. If you hold an apple made of antimatter and drop it, general relativity says it must fall down exactly like a normal apple. Gravity couples to energy and mass, and antimatter has positive mass. However, some extensions to the standard model of particle physics, and some theories of quantum gravity, suggest that this might not be strictly true. Some theories propose gravivector or graviscalar fields that could couple differently to matter and antimatter. If antimatter falls slightly faster, slightly slower, or even upwards, suggesting anti-gravity, it would shatter Einstein's theory. It would require a complete rewrite of our understanding of the universe, and could instantly solve the mystery of dark energy and the missing antimatter. To test this, we need an antimatter apple. And that is where positronium comes in. You might ask, why not just drop a positron? Testing gravity on charged particles like bare positrons is actually impossible. The electromagnetic force is 10 to the power of 36 times stronger than gravity. A stray electric field from a single wire meters away would overwhelm the gravitational pull of the entire Earth. To test gravity, you need a neutral atom. Most antimatter gravity experiments, like the alpha and GBAR experiments at CERN, use antihydrogen. An antihydrogen atom consists of a negative antiproton orbited by a positive positron. It is neutral and stable in a vacuum. However, antihydrogen has a dirty secret. The antiproton is a hadron, a composite particle made of 3 antiquarks held together by gluons. In fact, 99% of the mass of an antiproton comes from the binding energy of the gluons, not the antiquarks themselves. Since binding energy is just energy, and energy acts like matter gravitationally, even if true antimatter felt antigravity, the effect in antihydrogen might be diluted by the massive amount of binding energy which behaves normally. Positronium is different. It is a bound state of an electron and a positron. No protons, no neutrons, no quarks, no gluons. It is a purely leptonic system. Both the electron and positron are fundamental point particles. It is the lightest possible atom, and it is a true binary system of matter and antimatter with a 50-50 split. If there is a specific fifth force that acts differently on matter and antimatter, positronium is the cleanest, most sensitive laboratory to find it. But positronium has a fatal flaw. It is unstable. In its ortho state, where the spins of the particles are parallel, it lives for only 142 nanoseconds. That is 142 billionths of a second. In that fleeting moment, it zips around at thermal speeds of tens of kilometers per second before the electron and positron collide, annihilating into 3 gamma rays. How do you measure the gravity of something that moves at lightning speed and vanishes before you can blink? You have to freeze it. Cooling atoms is a standard technique in modern physics. We routinely cool rubidium and cesium atoms to microkelvin temperatures to build atomic clocks using a method called Doppler laser cooling. Imagine an atom as a bowling ball rolling toward you. You are standing with a tennis ball machine, which represents the laser. If you shoot tennis balls or photons at the bowling ball, each impact slows it down slightly. The atom absorbs a photon from the laser beam, transferring momentum to the atom and pushing against its motion. The atom then quickly re-emits the photon in a random direction. Over many cycles, the kicks from emission average out to 0, but the kicks from absorption, which always come from the laser beam opposing motion, add up. To ensure the atom only absorbs photons when it is moving toward the laser frequency is tuned slightly below the atom's resonance. Due to the Doppler effect, an atom moving toward the laser sees the light shifted up into resonance and absorbs it. An atom moving away sees it shifted further down and ignores it. Applying this to positronium is fiendishly difficult for 3 reasons. First is mass. Positronium is incredibly light, about 1/1000th the mass of a hydrogen atom. When it absorbs a photon, it doesn't just slow down, it recoils violently. The kick is huge, making the cooling process chaotic. Second is lifetime. You only have 142 nanoseconds. In standard laser cooling, you need thousands of absorption and emission cycles to slow an atom down. With positronium, you have to cram all those cycles into a blink of an eye. Third is the UV barrier. The laser light needed to cool positronium is in the deep ultraviolet at 243 nanometers. Creating high-power, long-pulse lasers at this specific wavelength is a massive technological hurdle. This brings us to the Aegis breakthrough at CERN. For years, the Aegis team has been working to tame positronium. In early 2024, they announced success using a specific type of laser called an Alexandrite laser. Standard laser cooling uses narrowband lasers, which are very precise, single-color lights. But positronium atoms, when first created, are hot. They move at a vast range of speeds. A narrowband laser would only catch a tiny fraction of them. Because positronium lives for such a short time, you cannot afford to wait for the atoms to naturally drift into the right speed range. You need to cool them all, and now. The Aegis team developed a broadband laser system. This laser doesn't emit a single sharp frequency. It emits a fuzzy range of frequencies. This creates a snowplow effect. The broadband light acts like a wide net, interacting with a large portion of the positronium cloud simultaneously, regardless of their exact velocity. By firing this broadband laser at a cloud of positronium produced in a nanochannel silicon target, AEGIS managed to drop the temperature of the sample from 380 Kelvin, which is hotter than boiling water, to 170 Kelvin, or about -103 degrees Celsius. While Aegis was using the shotgun approach of broadband cooling, a team at the University of Tokyo took a sniper approach. Their results, published around the same time, used a technique called chirp cooling. In chirp cooling, the laser frequency is not static. It changes, or chirps, over time. The laser starts at a frequency designed to catch the fastest moving atoms. As those atoms slow down, the laser frequency rapidly sweeps to stay in resonance with them. It essentially chases the atoms down the velocity curve, constantly applying braking pressure as they decelerate. The Tokyo team managed to cool their positronium gas to just 1 Kelvin or minus 272 degrees Celsius. These achievements are complementary. Future experiments will likely combine them, using broadband lasers to do the heavy lifting of initial cooling, and chirp lasers to finish the job and reach ultra-cold temperatures. Now that we can cool positronium, how do we actually measure gravity? We cannot simply watch it fall. In 142 nanoseconds, a positronium atom falling under Earth's gravity would move less than the width of an atomic nucleus. The solution lies in quantum interferometry and Rydberg states. To extend the life of the atom, scientists use lasers to excite the positronium into a Rydberg state. This means the electron and positron are pushed into a high-energy orbit, far away from each other. In this state, they rarely meet to annihilate, extending the lifetime from nanoseconds to milliseconds. A millisecond is an eternity in particle physics, and enough time for gravity to have a measurable effect. The AEGIIS experiment plans to use a device called a moire deflectometer. A beam of cold Rydberg positronium is fired horizontally through a series of gratings or slits. These gratings create a shadow pattern on a detector at the far end. If the positronium falls due to gravity as it flies through the device, the shadow pattern will shift vertically. If the pattern shifts down by the expected amount, Einstein is right. If it shifts down too fast, too slow, or miraculously shifts up, we have discovered new physics. The implications of positronium cooling extend even beyond gravity. One of the most futuristic possibilities is the creation of a Bose-Einstein condensate, or BEC, of antimatter. A BEC is a state of matter formed when atoms are cooled to near absolute zero, causing their quantum wave functions to expand and overlap until the entire cloud behaves as a single superatom. Because positronium is so light, its critical temperature for becoming a BEC is much higher than for normal atoms, potentially achievable at 10 to 20 Kelvin. If you can create a BEC of positronium, you force all the atoms into the same quantum state. When they inevitably annihilate, they would do so in unison. Normal annihilation produces incoherent gamma rays, which is just random light. BEC annihilation would produce coherent gamma rays. This is essentially a gamma-ray laser. Current lasers produce visible, UV or X-ray light. A gamma-ray laser would be orders of magnitude more energetic. It would allow us to peer into the nucleus of atoms, manipulate nuclear states for new forms of energy, and probe the fundamental limits of the Standard Model. Aegis is not alone in this race. CERN's Antimatter factory is a bustling hub of competition. The Alpha-G experiment uses antihydrogen, and recently confirmed that it falls downward with an acceleration consistent with 1 gram, ruling out strong anti-gravity. However, Aegis is unique in its focus on positronium as the direct test subject. The breakthrough in laser cooling puts Aegis back in the pole position for a high-precision measurement on a purely leptonic system. While Alpha-G has verified the sign of gravity, Aegis aims to measure the magnitude with enough precision to test specific quantum gravity theories. The successful laser cooling of positronium is a triumph of human ingenuity. We are now entering the era of precision antimatter physics. We are moving from simply making antimatter to mastering it. We can slow it, trap it, cool it, and manipulate it. In the coming years, we will see the temperature drop from 170 Kelvin to 10 Kelvin and eventually to the sub-Kelvin regime. If scientists find that gravity for antimatter is 9.81 meters per second squared, Einstein will be vindicated once again. But if they find it is 9.7, or 9.9, or negative 9.8, the textbooks will burn. The universe will be stranger than we imagined, and a new golden age of physics will begin. For now, the antimatter is freezing, and the world is watching. Thanks for listening to G Fun Facts Online.